Here is a complete instruction of getting temperature from STM32 internal sensor. Open STM32 CubeIDE. Press File, New, STM32 project. Type your microcontroller's part number. I used STM32F401CCU6. This microcontroller is used on the black pill module. Press Next. Type any project name. Press Finish. Press Ctrl M. Enable debugger. To do this, select on System Core Sys Debug Serial Wire. There are two pins is used for serial wire, clock and data. Let's enable external crystal. In RCC, choose high speed clock resonator, crystal ceramic resonator. Go to clock configuration. In the black pill module, crystal is 25 MHz. Choose high speed external, choose PLL clock, enable CSS and type maximum frequency 84. Press enter. Wait for searching solution. That's okay. Go back to the pinout and configuration tab. Now go to the analog ADC one. This microcontroller have got only one ADC. Now you can see many channels. These channels can be connected to the microcontroller's pins, but we need temperature sensor channel that connected internally. Choose temperature sensor channel and Vref int channel. This channel makes possible to measurement real voltage supply. This can be very useful when microcontroller is power up from the, for example, lithium battery. So now we have two internal channels. Let's configure the ADC. Press on the DMA settings, press Add, select ADC1 and choose mode circular. Data width is half watt. That is uint16T. Go to NVIC settings and enable global interrupt, which help us to know when the conversion is completed. Go to the parameter settings. Enable scan conversion mode that makes possible to get measurements from a few channels. Enable also DMA continuous requests, and continuous conversion mode also should be enabled. Number of conversion is 1, but we already enabled 2 channels, so change it to the 2. Now we have 2 channels with different rank. Rank 1, rank 2. Let rank 2 is Vref int channel and the second one is channel temperature sensor. Choose maximum sampling rate. In the external trigger conversion source, we can choose regular conversion launch by software, but I prefer launch by the timer out event. So I choose timer 3 trigger out event. This timer will be trigger ADC conversion, so we need to configure it. Go to the timers, team 3. Enable internal clock. Go to the clock configuration. As you can see, all timer clocks bus, advanced peripheral bus, is clocked by the same frequency, 84 MHz. So open calculator, type 84 MHz and divide it by the frequency that you need. For example, I need 10 Hz. Now we have this number. This number must be divided by the prescaler and auto reload register. But note that is the maximum value of this register is 65,535. So divide it by the 814 and type it. Then we have 10,000. Type it. Why -1? Because if we type 0, can be divided by 0. The 0 is meaning divide by 1. And trigger event selection must be update event. That's all. To generate the code, you can press on this gear or Alt plus K. Press yes. To build the project, right-click, Build Project. In the Private Variable section, create UIN16T array half-watt ADC row that consists 2 elements. Before main loop, start ADC with the DMA. We use ADC1, pointer to the data is UIN32, so the name of our array, ADC row, and length. We have 2 channels, so length must be 2. Then we need to start timer that trigger ADC. This is timer 3. That's all. As you can see, we do not have code in the main loop. Press Build Project. Now we can debug our code. Press Debug S, STM32 Cortex-M application. We can check if the debugger is successfully identified. Go to the debugger, ST-Link, scan, and we have it. Also, you can check your ST-Link, press Win plus R, type def mgmt MSC, press OK. This opens Device Manager, and in the Universal Serial Bus Devices, you will see STM32 ST-Link if it connected and the drivers is installed. So press Apply and OK. Press Switch. Before launch the code, press Ctrl+3 and type love expressions. In this window you can type any global variables and monitor it during the program is executed at ADC row array. You can open it, and now we launch the program. As you can see, ADC works fine, and we get measurements from the ADC. The second one is from Vref int channel, the second one is from temperature sensor channel. Let's check it. Yes, Vref int channel first, and second is channel temperature sensor. In the cube settings we turn on interrupt from the ADC. So let's add callback function. You can find it in drivers, HAL driver, SRC, HAL ADC. This is a pretty big file, but you can open the outline, press Ctrl+3 and type outline. In the end of the list you can find many callbacks. We need conversion complete callback. Copy this function. Go to the main C, go to the end of the file and create it. We have one ADC, but if a chip has a few ADC, we can check where interrupt is come from. So HADC instance is equal to the ADC1. Let's create in the private variables a global variable flag and set it to the 0. Now let's add the breakpoint. You can Ctrl+Shift+V or double click on the left. So let's compile the project, build project, and in the main cycle we can check if this variable is true, that is mean the conversion is successfully complete. We do something and then nullify this variable. So build project and let's debug it. Debug as STM32 application. We can also add to live expression this variable and let's start the program. As you can see, we end in the conversion complete callback and conversion is successfully completed. Let's resume. We have new values and we again enter in this function. Let's remove the breakpoint and resume the program. As we can see, we get new values from the ADC, and ADC conversion complete flag is updated, but it's pretty high frequency, so we do not see that. But we can add the breakpoint in the loop cycle. Yes, it works. Again, it works successful. So let's go to the next stage, because we already have ADC values and we exactly know when conversion is completed. Now let's find the datasheet on the microcontroller. Type portable file document site st.com. Here it is. Let's find embedded reference voltage. As we can see, typical value is 1.21 volts. Let's define this value. As we previously choose ADC row 0 element according to the 1.21 volts, so let's calculate the real supply voltage. The maximum value of the 20-bit ADC 4095. Now it's defined by the macros. Let's use it. So Vref int multiply by ADC max and divide by measured value. Let's build the project. One warning, because we don't use this local variable. It's okay. Let's set a breakpoint. Debug. Resume. One calculation was done, and as we can see, real supply voltage is 3.15 volts, and as you can see, it is very similar to the real voltage measured by the multimeter. It works good. Now let's find reference manual. This is a pretty big document. Find temperature sensor section, and as you can see, supported temperature range and precision. This sensor is pretty raw. And now we see the formula and a few of constants. This constants is available in the datasheet in the temperature sensor characteristic section. So we have voltage at 25 degrees, let's define it. Also we have average slope 2.5 millivolts. So this is a 0.0025 volts. That's all. Now let's calculate temperature sensor's voltage. Double V temperature sense. And if we don't use internal reference channel, we can just type 3.3 volts, because it's a typical supply voltage for this chip. But we have got a real supply voltage, so we use Vref int variable. Multiply by ADC row first element and divide by maximum ADC value. Let's build a project and debug it. Start the program, and as you can see, temperature sensor voltage is 0.76 volts, and according to the datasheet, the voltage at the 25 degrees must be the same. So we can suggest that internal sensor works properly. And now let's calculate temperature. We have formula double temperature, we sense sensor voltage minus voltage at the 25 degrees. This is defined V25 divided by the average slope, and we already have average slope in volts, and V temperature sensor the same in the volts plus 25 degrees. Let's build the project. Error, small error. Of course, we can't use volts here. So let's build the project. Unused variable, it's okay. Breakpoint was set, and we can terminate and relaunch. Start the program, and 28 degrees, it's pretty good value. We can do calculation and measurement again. This is a local variable, so we can copy temperature sensor and create a global variable. Build project, debug application. Open live expressions and add temperature variable. Start the program. And now we can Remove all breakpoints. Remove. Start the program. Now we have temperature value. It works pretty good. As you can see, get temperature from the internal sensor is not a big deal. But for convenient use, I have created a small library that have already constant values and only one function, get temperature. As you can see, the first argument it's sensor's temperature channel ADC value. The second one it's reference channel value, and it's return a calculated temperature. And in real project, it's more convenient to use library. To find out project location, right-click on the project name. Show in System Explorer. Open the folder. Open Debug folder. There should be an ELF file. Copy current location. Open STM32 CubeMonitor. Let's check that ST-Link is successfully identified. Press Win+R and type dev.mgmt.msc. Click OK and Device Manager will open. In the Universal Serial Bus Devices section, find STM32 ST-Link. This is a default set of blocks. Double-click on My Probe Out. Here you need to select the debugger, but you have to add it first. Click on the pencil. Select your successfully identified debugger. Choose protocol serial via debug and the left default frequency. Click Add. Now you can check connection. Click on the bulb and LED on the ST-Link will be blink. Click on the My Variables block. Now you have to choose previously find executable ELF file. Paste folder destination previously copied and choose ELF file of your project. In the variable list, find variable that you need to monitor. This variable must be global. If the list is too big, use the search below. Click Update and Done. Double-click on My Probe in block. Here you also have to choose previously added and choose ST-Link probe. Double-click on My Variables processing block. Here you can see all variables that you add previously. Here you can do mathematical transformation. I often use average function to get more smooth curve. So I check it and click Add Statistic. Now this variables is added to outputs with post-processing. Also you can check out chart configurations. Let's change duration from 20 seconds to 15 seconds. Click Deploy. If ST-Link is successfully connected, you will see P2P connected. Then click on Dashboard button. Chart now is available. Start acquisition. So that's all. Now we can monitor global variable. These variables contain temperature from internal sensor. The data can be saved and then analyzed. So let's make an interesting test and heat up chip by the hot air gun. Well, the STM32 CubeMonitor is running and displays the temperature of the internal storage. When it heats up, the value increases, so monitoring works. The datasheet specifies the allowable operation ambient temperature range. Minimum operation temperature is minus 40 degrees. Maximum operation temperature can be plus 125 Celsius degrees. Maximum junction temperature is plus 130 degrees. This is the internal temperature of the chip die. Now I turn the temperature up and it's now already over allowable range, but chip still works. Heating continues. Microcontroller still works and we are getting measurements. When temperature reach about 240 Celsius degrees, the debugger don't send data and acquisition stops. But if we press start again, acquisition continues. As we can see, STM32 withstands significant oven temperature without complete failure and get back to work without problems. So, now you can use internal temperature sensor in your STM32 project, and a full code you can get on GitHub, links in the description.